All right, everyone. Hello. My name is Jeremy, and I am the CEO of RISC Zero. And today I'm going to be sort of speaking through a little bit about where the state of our system is, as well as sort of a lot of different use cases and real-world applications that people are building on top of the RISC Zero system. My talk slide here. So it's really about sort of the fact that, RISC Zero, with the release of the ZKVM 1.0, is now really production ready for a lot of real-world use cases. Just in terms of the agenda, I'm going to briefly cover sort of a little bit of background on RISC Zero and what it is we're building. Many of you may already know some of this, so please bear with me. And then we're going to talk about sort of where we are in the space, and then go into a bunch of different use cases, scalability, privacy, some additional things, and then sort of cover where things are heading from here. So just quick background on what exactly is RISC Zero, in case some of you don't know. I'm going to kind of speed run this section a little bit. But I think we're all basically familiar with what a zero-knowledge proof is. But I think fundamentally it's very interesting the power that zero knowledge has, because it lets you show that something is true without explaining all the details that you used to show that it's true. And what's really interesting from a scaling perspective is that you can do this in a way that doesn't require whoever's checking your results to do the full work. And one of the things that ZKP has been around for quite a while, but in addition to performance issues, one of the big limiting factors in terms of people applying it to real-world use cases has really been about the process of programming zero-knowledge proofs. And largely this was because the original sort of way to do this was to take your high-level thing you wanted to show was true and translating it into a system of polynomial constraints over finite field elements, which is about as programmer-friendly as it sounds. And this sort of, I think, it was the state of the art for quite a long time in the industry. And recently, though, there's been a movement, and we're one of the sort of, people helping this progress along with the idea of a zero-knowledge virtual machine. And the theory with this is that you have one party, in this case us, build a circuit that, in fact, actually operates a virtual machine. At that point, you can take ordinary code, compile it down, and then run it in this zero-knowledge virtual machine and get a proof. The key thing here is that you're moving the process of describing what it is you want to prove in zero knowledge into the process of writing ordinary code instead of the process of writing a circuit, which is much more developer intensive. And I think that when you look at the advantages this brings, it makes the ability to program much, much, much easier, and it's very general purpose. In our particular case, one of RISC Zero's innovations was taking and making our zero-knowledge virtual machine actually a standard industry ISA, basically the risc-v ISA. And by doing so, what that means is that many existing languages, in particular Rust, can in fact be compiled down and run on the zero-knowledge virtual machine. And so what that means is that you can actually just use normal Rust code to do your zero-knowledge proofs. And that means you can, more importantly, rely on the Rust ecosystem. So, in this chess example here, we're actually pulling in a bunch of existing, chess libraries, right? So what that means is that you suddenly have access to a huge amount of capacity through the existing ecosystem. And then, of course, one of the key points is that you can then use these zero-knowledge proofs and verify them on chain. So I wanted to talk quickly about sort of where RISC Zero as a product is. And one of the key things is that we are absolutely production ready. We have a stable prover and guest APIs. So if you build something on the ZKVM 1.0, you can rely on that being supported moving forward for all of eternity. We have completed all of our public setup ceremonies, and we have verifier contracts running on many of the main nets, and we will continue to increase this list with the goal of basically being able to verify RISC Zero proofs on more or less any blockchain, right? From the security perspective, we've had audits of every component of the system, the ZKVM 1.0 prover and verifier themselves, the risc-v circuit that is the ZKVM, the mechanism by which we do our on-chain verification, which is a snark-to-snark mechanism, our on-chain contracts, and most importantly, we have a very rigorous security process in terms of the way that we do releases, internal reviews. I think we have a very high level of rigor, and really the key takeaway is when I say that this is ready for production, I mean go lock tens of millions or hundreds of millions of dollars behind contracts using the ZKVM as verification. We're ready to stand behind that, right? So we believe this is absolutely usable in production now. And in terms of performance, we really have the best performance of any ZKVM in the industry. We recently released some new performance numbers. We have really excellent GPU acceleration of proving. And so we're actually able to do 500 kilohertz of risc-v proofs per second on a GPU. One of the key things is not only is our performance fast in terms of wall clock time, but we've done a lot to optimize sort of cost efficiency. At this point, you can actually run, Reth basically Zeth is what we call it, when you basically run to prove an Ethereum block inside the ZKVM is actually now under $1. And we have like less than 1 second of recursion time. So I think that our performance is pretty hard to beat. So I guess now that I've sort of talked about the status of where we are as a product, I kind of wanted to cover some interesting use cases. So I think one of the key and most obvious use case of a lot of zero knowledge is the proving of a state transition function, right? So if you look at L2s and rollups, there's a number of people that are actually building on our system right now. So clearly in the case of a ZKL2, what you're going to be doing is proving the correctness of your state transitions so that each state transition is ZK verifiable. What's interesting is that even for optimistic L2s, there's a lot of really excellent uses of ZK. So we're currently working with Optimism right now on sort of ZK fraud proofs. But the idea here is that if you look at sort of a typical optimistic stack, when someone makes a claim about a state transition that is incorrect, there's this sort of back and forth, game that has to be done by the different parties to sort of prove that they've incorrectly stated something. By using ZK, you can instead do a very single one-step process where you say, oh, you said that this is the correct answer for the state transition. Let me prove in ZK that the answer is actually something different, and then your fraud proof is a single round, right? So I think that this idea of mixing optimistic and ZK is something that will continue to happen. And of course, obviously, rollups are another sort of key use case for ZK, where you're proving the correctness of the state transition function again. And we have a number of different partners working to use our ZKVM for these use cases. The other sort of scalability use case is this sort of idea of a ZK coprocessor, which is rather than sort of have a separate stateful L2 or rollup that you're proving the correctness of. The idea with the ZK coprocessor is that you take some on-chain state and you prove some fact about it using the ZKVM, and you post that back on-chain. So, for example, if you look at a governance use case, maybe you want to sort of do the aggregation of all the votes and all the signature verifications. Well, it's very expensive on-chain. It costs a lot of gas. Instead of doing all of that work on-chain, you actually do all that work off-chain, prove the correctness of it, and then post the results on-chain. Similarly, for lots of DeFi use cases, you can imagine that there's some kind of a complex market-making mechanism, and maybe the gas cost to do all of that work on-chain is very high. Again, you can sort of offload that work to do off-chain in zero knowledge and then prove it on-chain. And I think one of the other key things to note is that in addition to the verifiability, one of the key points about our ZKVM is that it does support a lot of sort of privacy use cases. It does maintain that sort of zero knowledge property. Actually, one of the weird things about this industry is there are lots of places where people use the term zero knowledge to really mean verifiable computing. And so a lot of things that are called zero knowledge are not in fact privacy preserving, but our ZKVM is in fact. I think that when you start looking at the ideas of what you can do with this zero knowledge mechanism, there's a lot of really cool things to do. One of the use cases is, for example, this idea of ZK login, wherein what you're doing is you're allowing people to use single sign-on mechanisms even in a blockchain context. And the way that this works under the hood is that when you log in with Google, for example, Google is basically signing a document with Google's keys that says that you have correctly logged in, that some third party can check. In this case, we can actually verify that document within the ZK VM and produce a ZKP, which includes the potentially redacted information about you. So Google may say a bunch of things about you, but you may want to just show that your Google thinks you're over 18 or whatever the case may be, or Apple thinks that you're a real person. That's one of the pieces of metadata on their JWT login is likely real person. So this is cool because it brings a lot of the existing sort of identity infrastructure that is part of Web 2 into sort of the Web 3 use cases. Interestingly, another interesting use case is actually that most modern passports, in fact, have full signed signatures on them from the country of origin that in fact verifies all of the passport metadata, including even things like the image and biometrics and things like that. Now what's interesting is that you can then again do the same thing where you have someone take all of this data and then do a ZKP to verify the correctness of these documents, but then redact whatever you would like. So, for example, you can make an actual zero-knowledge proof that shows that I am a citizen of the U.S. and my age is over 30 without providing any other information, right? So I think that's a really useful ability. And here's another funny example. This is a little demo we put together, proof of accredited investorship, wherein we are basically actually walking through and parsing documents from the IRS, and then using that to provide zero knowledge proof of some useful capability from that. So a lot of different cool use cases. I'm just going to cover some other sort of use cases that people are either working on or have been discussed that I think are very interesting, but I won't really have enough time to get into in detail. But basically, obviously ZKML, because we are, of course, a general purpose computing thing, we can do things with floating point numbers. We can run arbitrary existing ML, crates from Rust. There's a lot of use for ZK for bridging and light clients. In many cases, you can just literally run the light client within the ZK VM. There's lots of gaming applications. Actually, a funny one, proof of exploit. This is where you make a zero-knowledge proof that you have some input that would cause an exploit to occur on some existing, say, smart contract or some other code, and then but you don't reveal what how you exploited it, but you can prove that you were able to exploit something. Even things like verifiable compilation, right? Because we're our general purpose computing, you can run arbitrary things, you can run a compiler and show that this code, in fact, compiles to that thing, et cetera, et cetera. So. And then I just kind of wanted to start talking a little bit about what's sort of next in terms of where we're going at RISC Zero. So, we actually have a performance roadmap to continue to improve our performance. We are already the sort of industry leader in terms of our current performance metrics, but, I think that fundamentally as ZK gets faster and faster, it unlocks more and more use cases that used to be economically infeasible to do with ZK that are now becoming feasible. We're also going to be adding support for more accelerators for certain key cryptographic operations, and also a third-party accelerator framework so that people can add custom circuit acceleration for other operations. I think the most interesting one, though, is that we are very shortly going to start discussing publicly work that we've been doing internally on a network to allow people who want proofs done and people who want to do proofs to connect. So we are looking for early adopters for the prover network. So people who are interested in doing sort of building applications that rely on zero knowledge, as well as people who are interested in running proving hardware should definitely talk to us. We have a certain limited number of people we will be onboarding for that process in the near term. But this is something to, we will be announcing more details of later. So pay it, keep watching for us on Twitter and stuff. Anyway, that was my talk. I wanted to give a couple minutes for questions. And we have a lot of events going on at EthCC here. This link here will keep you up to speed with all those different things that are going on. There's some contact information for me. All right. Do we have time for questions? Yeah, cool, awesome. Go ahead.
Thanks, Jeremy. So you mentioned the brewer cost is about under $1 for a block. This is assuming that you have to the recursion layer and put it have verification.
Well, I mean, so generally when you run larger programs, we use recursion automatically. There's two different costs to consider when you're considering ZKPs. One is the cost of doing the proving, and one is the cost of doing the verification of the proof on the blockchain. And yes, actually, it depends upon what blockchain you're looking at. On ETH-L1, I think currently our verification costs are probably north of $1. Like I think it's like about 300K of gas. That said, we are as part of the proving network, we will be providing mechanisms to do aggregation, which will bring down the verification costs on a per proof basis down dramatically. But yes, what that cost I was referring to there was the cost of generating the proof, not the cost of verifying the proof.
Generating the proof plus the recursion.
Yes, plus the work necessary to put it online. Actually, most of that's the amount of work at the end to prepare it for blockchain verification is a very small amount of work in terms of dollars.
There was this performance slide that you where you gave perspective versus SP1, and it's written SHA and FIB and sort. Can you give more detail on like the exact benchmark we're talking about?
Yeah, so the sorting benchmark reads in a bunch of random numbers and performs whatever Rust's default sort mechanism is, I believe. It's largely, go ahead.
I mean the size of the input is kind of a question. Like for instance, let's take SHA-2. What is like the number of hash being computed in the benchmark?
So I think this one was sort of a middle range one. We actually have the full details from very small examples to very large examples. This was sort of the middle of the range. Actually, on the smaller end, we actually have even larger performance gains, and then it sort of trails off to about. But we remain more performant than SP1 across the entire board for more or less all the examples. But we have a blog post out that goes through all of the details. It's got a huge spreadsheet, so you're welcome to dig in as much as you would like.
I think I looked it up and I couldn't find it, but okay, I will talk to you after that.
Absolutely, happy to.
And just one other question then about the 500 kilohertz performance. Do you have the same metric for a single thread on a CPU, or it's not like they could?
So most of our performance is very heavily based on GPU acceleration, and so when we performed the comparisons, what we do is we run our prover on our preferred sort of hardware setup on Amazon, for example. So when we look at cloud performance, we run our prover on AWS using a GPU-based machine, and then when we run, say, SP1 for comparison, we pick their preferred machine, and then we look at the performance per cost normalized. One of the tricky things about this industry from a performance metric standpoint is that because different proof systems sort of want to be optimized for different kinds of machines, in order to really get fair comparisons, you have to kind of run each prover on its preferred environment and then sort of normalize for cost, right? So.
So the 500 kilohertz benchmark for clock speed.
Yes.
I think a year ago it was like 100 kilohertz or something
Yes.
like that. So it went from the 1960s, pre-Intel processor to the 1970s in the course of 1 year. But
Yes.
do you have any projections over the next couple of years of where you guys can get to in terms of clock speed?
Yeah, so I think that so there's on a single GPU right now, we're north of 500, and I think that over the next quarter we will probably see at least a 2 to 3x of that. And then I think beyond that, there's definitely room for even further improvements. I would not be surprised if a year from now it were on the order of 5 or 10x. Beyond that, you start to get into sort of the fundamental barriers that I think are going to be harder to overcome but beyond custom hardware. But I do think there's still quite a lot of room. And then beyond that, there's lots of places where there are parts of the work that is acceleratable, particularly cryptographic operations, where by building sort of this accelerator framework, those cryptographically intense operations, instead of running them on the RISC-V ISA as software, those would get actually moved into the circuit. In many of those cases, those accelerations, are on the order of, 20, 50x performance improvements over the running it inside of the VM directly. So,
are there just to follow on with a 1B question? Are there any applications that become possible when you go from 500 kilohertz to to 5 megahertz or something like that?
Yeah, I mean, I think a lot of things like, so if you look at things like proof of compilation or other things like that, you're looking at much larger, program execution times. And one thing to note too is those numbers are, we actually get we get into the tens of megahertz speeds on a network level within like our existing sort of cloud Bonsai version, because we were able to parallelize this work across multiple devices. But I think that largely what's interesting is that I think speed is a bit of speed does matter and latency matters, but I think if you look at most of the sort of new emerging applications, the real critical fact is related mostly to the cost. How much does it cost to generate a proof? And as that number goes down, that's really where the bigger unlocks, I think, come from. And there's actually even more room for cost performance metrics, because you can do optimizations which don't really improve your wall clock time, but they reduce the amount of watts things take, or they allow you to run on lower spec hardware. So.
Like non-freestanding code in any way in these VMs? So like you're talking about verifiable compilation.
Mm-hmm.
Is that a compiler that is perhaps freestanding itself, or can you?
Yeah, I mean, so I think maybe to answer to sort of get at this question, I think there's the one question is sort of how pure like does the code have to be in terms of calling system calls and so on. So in the current version, it is true that most of the sort of system calls to access file systems or things like that are going to just return errors, basically. Okay. That said, we are actually the version 2 of what we're working on. We are working on mechanisms to allow a lot of those kinds of use cases to be a little bit more seamless. Right now it is like regular programming, and many, like I think more than 70% of the crates on the top 1,000 crates work right out of the box. But it is, not a full-fledged environment. Like obviously you can't open up network connections within the ZK VM and so on. So yeah, if that hopefully answers your question. Yeah, cool. Okay. All right. Well, thank you everyone. Have a great day.